Section 4.5. The experimental determination of delta U and delta H for chemical reactions. It seems to be simple. If we do a reaction and measure the heat of the reaction, it is delta U if the condition is constant temperature and constant volume. It is delta H if the condition is constant temperature and constant pressure. However, sometimes we need to know delta H, but can only measure the reaction under the constant temperature and volume condition. And then how can we get delta H from delta U? Now let's look at one experimental apparatus. We will combust this sample in this reaction vessel. It's called a bomb. This bomb can withstand very high pressure and very high temperature. So the reaction will be ignited by this ignition box. This ignition box sends electric current to the sample, ignite the sample, and then heat is released from the combustion reaction inside the bomb. The heat is dissipated into the water bath. So what we need to do is simply measure the temperature change of the water bath. If we know the heat capacity of the water bath plus the heat capacity of this bomb and everything else inside this calorimeter, we will be able to compute the amount of heat released from the combustion of the sample. And when that's the case, we divide the amount of heat by the number of moles of the sample. We will get the internal energy of the reaction. And then somehow we have to compute this delta H of the reaction given delta U of the reaction. Oh, by the way, this bomb is providing an isochloric environment. That means constant volume. Therefore, Q is equal to delta U. So how can we compute delta H given delta U? Well, H is equal to U plus PV. That's the definition of H. And then we can separate this two. We have delta U here. We have delta PV here. How do we compute or measure delta PV? It's very difficult. However, one thing we know, this is the change of the product of PV. If we have solids, liquids, and gases in a system, the PV change of liquids and solids is negligible because the volume of liquids and solids is negligible compared with gases. So look, I'm adding the gases here. We just need to worry about the PV change of the gases. The reason is as follows. We can use PV equals nRT approximation here, right? Of course, it's not going to be accurate because real gases are involved. However, this approximation is good enough for this purpose. And then we know that this N of gases may change. Why? This number of moles of gases depends on the coefficients in front of the gases in the chemical reaction. It may change. For example, if you have hydrogen react with oxygen to produce water, well, the number of gases changes from 3 to 0, assuming you have 2H2 plus 1O2 to produce liquid water. Now, we can assume the temperature is a constant. You may wonder, this is combustion, heat is released. How can we assume temperature is constant? The reason is simple. We use a very large amount of water to absorb the heat. So even if a lot of heat is released, the temperature change is minimal. For example, the initial temperature is 25 degrees Celsius. The final temperature is only 27 degrees Celsius. So no matter you use 298 K or 300 K as the temperature, this delta nRT is roughly the same. Therefore, over here, approximately, we assume the temperature is constant. And then delta H is simply delta U plus RT times delta N gases. R is 8.314. T is the reaction temperature. Again, even if you use the initial temperature or the final temperature or taking the average, it doesn't really matter, or any temperature within the temperature range, you will see it's not going to affect your result, because anyway, this term is much smaller than this term. And then delta N gases comes from the coefficients in front of the gases involved in the chemical reaction. Typically, for combustion reactions, delta U and delta H are negative thousands of kilojoule per mole, while this RT delta N gases is only a few kilojoule per mole. Therefore, again, if we use the initial temperature or the final temperature, well, that will affect this a few kilojoule per mole by just a few percent. So that's going to be roughly 0.05, 0.02 kilojoule per mole. Now compare 0.02 with 1,000. Well, that's negligible. A reminder here, delta N gases is unitless. This is because delta N gases is the change of the number of moles of gases per mole reaction. So really, this delta N gases is the coefficients in front of the gaseous products minus the coefficients in front of the gaseous reactants. They are unitless. Now, how do we determine this delta U of the reaction experimentally? Well, that's easy. We just measure the reaction heat. The reaction heat is the number of moles of the samples times delta U. Therefore, delta U is simply heat divided by the number of moles of the samples. I put this vertical bars here. They are the absolute values. This is because it's a little tricky here. When a sample is combusted, delta U is negative, but heat flows into the water bath, the calorimeter. So for the water bath, the Q is positive. Again, it just with the sign of the Q depends on what system we're talking about. If we're talking about the sample, Q is negative. If we're talking about the water bath, Q is positive. So just to make it simpler, I'm using the absolute values here. And then how do we measure the amount of heat? Well, it's simple. We just need to know the heat capacity of the water bath and the calorimeter, because both absorb the heat released from the sample. Therefore, we take the sum of the heat capacity of everything inside the calorimeter that absorbs heat. We measure the temperature change. The product of the temperature change and the total heat capacity is going to be the heat flow. This C of the calorimeter is called the calorimeter constant. How do we measure this one? Well, if you purchase a calorimeter, this constant is provided by the manufacturer, but also we can measure this. How do we measure this C of the calorimeter? We need a standard. We need a chemical with known enthalpy of combustion, and then we calibrate. For example, we use benzoic acid. We know the enthalpy of combustion of benzoic acid is this much. And then we can compute the internal energy of combustion, which is roughly 3,226 kilojoule per mole, a little different. And then if we measure the amount of benzoic acid precisely, we will know how much heat is going to be released in the bomb under this isochoric condition. Again, the number of moles times the standard internal energy of combustion will give us the amount of heat released from that benzoic acid sample. If we know the amount of heat divided by delta T, that will give us the heat capacity of water plus the heat capacity of calorimeter. And somehow we can determine the heat capacity of water if we know the amount of water. So we just need to measure amount of water exactly. And we know the heat capacity of 1 gram of water is 1 calorie per Kelvin, or 4.184 joule per Kelvin. All right, so that's how we determine the calorimeter constant using a standard chemical. Typically, it's benzoic acid. So in the actual bomb calorimeter lab, we don't usually determine the C of calorimeter because we're going to just use benzoic acid to determine this C, the sum or the total heat capacity. That's it. And then we just need to use this C to determine the internal energy of combustion of a unknown compound. But make sure we use the same amount of water in every single trial. That's important, so that this C remains unchanged. Now let's look at one example problem. Let's look at benzoic acid. Let's combust 1 gram benzoic acid and determine the calorimeter constant. First, write out the equation. The reason is we need to know the coefficients in front of the gases. 7 CO2 versus 7.5 O2. The change of the number of mole gases per mole reaction is negative 0.5. Again, it's negative 0.5. And then we have this equation. Delta U is delta H minus delta PV. Delta PV is RT delta N gases. We derived this. And then we plug in all the numbers. And this time when we use R, this is our R in kilojoule per mole K. Okay, so over here, this is in kilojoule per mole. So when we use the value of R, we use 0.008 kilojoule per mole K. The result is 3226, a little different from 3227. All right, and then to compute C, we need to multiply this standard internal energy of the combustion reaction with the number of moles. So this product is the amount of heat released from the combustion of 1 gram benzoic acid. Divided by the temperature change, we have the heat capacity, 6.61. And then we just subtract this heat capacity of 1 kilogram of water, which is 4.184 kilojoule per Kelvin. And then we have 2.43 kilojoule per Kelvin. This is the heat capacity of the calorimeter, or calorimeter constant. I also want to mention that when we are talking about the temperature change, 1 Kelvin is the same as 1 degree Celsius. The reason is simple. If you change your temperature from 25 to 26 degrees Celsius, the temperature change is 1 degree Celsius. Also, it's 1 Kelvin because you change the temperature from 298 K to 299 K. What's the temperature change? 1 Kelvin. So in this sense, 1 Kelvin is equal to 1 degree Celsius. Again, when we are talking about the change of the temperature, 1 Kelvin is equal to 1 degree Celsius.